Today we are going to do something a bit different. We are going to solve the Leetcode problem number 150, evaluate reverse Polish notation using a piece of computer science history. In 1957, the Australian philosopher, logician, and computer pioneer Charles Leonard Hamblin published the paper titled An Addressless Coding Scheme Based on Mathematical Notation, which pretty much solves this Leetcode question. You see, at that time, computers operated with a flat memory model, where programmers explicitly managed memory locations to store variables, parameters, and return addresses, which was slow, difficult, and expensive, and in Hamblin's words, made programming a modern digital computer a laborious and sometimes extremely complicated task. So a lot of work was being done by computer scientists of that time to develop new techniques, new notations, new languages to make programming faster and easier. Because computers were used to make calculations, the task of the programmer was essentially a task of translation from one already adequate language, namely the symbolism of ordinary mathematics, into a radically different one. So there was this desire to let programmers directly use mathematical notations. This is why the first high-level programming language was called Fortran, for formula translation. But a minor complication of algebraic symbolism concerned bracketing. So logicians have used a system of writing logical formula which eliminates brackets entirely, the so-called Polish notation, which consists in writing operator symbols in front of the operands. For example, a plus b becomes plus ab, or open parenthesis a plus b, close parenthesis, times c becomes times plus abc, and a plus open parenthesis b times c, close parenthesis, becomes plus a times bc. However, for machine use, this system has the disadvantage that the order in which the operator symbols occur in the formula is the reverse of the order in which the operations are supposed to be performed. As you can see in the examples below, the first operation that needs to be done appears last in the Polish notation. So it is perfectly feasible to use a reverse Polish notation in which the operators follow the operands. So a plus b becomes ab plus. The expression open parenthesis a plus b, close parenthesis, times c becomes ab plus c times. And a plus open parenthesis b times c, close parenthesis, becomes a, b, c times plus. So now, the order in which the operator symbols occur in the formula is the same as the order in which the operations are supposed to be performed. To evaluate an expression, each symbol of a formula can be regarded as a machine instruction. We can imagine that we have a number of storage locations arranged in a linear order. It refers to these locations collectively as the accumulator and individually as cells. So when a number is required for an arithmetic operation, it is placed in the first vacant cell. So cell 1 if this does not already contain a number, otherwise in cell 2. And when a dyadic operation such as addition or multiplication is carried out, it is always on the numbers most recently transferred in, that is, the numbers in the last two occupied cells. For example, the addition will be carried out by adding from the last occupied cell to the next last, the last cell being then emptied. So the result of any formula in reverse Polish notation will be in cell 1. Let's try with another example. We first see a 2, so we add it to the first cell of the accumulator. Then we have a 3, we add it to the second cell. Then we add the number 4 in cell 3. Now we see a multiplication. So we take the value inside the cell 3 and multiply the value of cell 2 with it. We now have 12 inside cell 2. And the cell 3 is empty. We keep going with the addition, so we take the value of the cell 2 and add it to cell 1. So now we're done and have the final result inside the first cell. So as you can see, the accumulator has a last in, first out behavior. Every time we see a number, we add it in the first vacant cell, and when we see an operator, we remove the last two elements and store the result of the operation in the first vacant cell. Let me repeat that. When we see an operator, we remove the last two elements and store the result of the operation in the first vacant cell. So it should appear clear that the accumulator is really just a stack. So we don't really need to keep track of the cells numbers or of vacant cells. We can just push or pop elements, and the final result is on top of that stack. This paper really describes a stack, and it goes a bit further by proposing to use the principle of this accumulator to execute subroutines, or in other words, to make function calls, by defining storage locations equaled a nesting register, which is pretty much what we know as the call stack. In my limited knowledge, the word stack was first introduced in 1960 by
Edgar Wijbe Dijkstra
in his paper Recursive Programming, in which he describes much precisely a call stack to make recursive functions possible by storing parameters, local variables, and what he called the link. And that's what he used to implement the first Algol 60 compiler, which later led to the development of computers like the B5000 in 1961, which was designed to compile Algol and COBOL into machine code written in Polish notation. And it did so by using several memory stacks and by providing stack registers. This marked the beginning of hardware implementing features to help the software. And this is why we now have modern CPUs with special registers and instructions to handle a stack. Okay, I think that's some pretty cool computer history right there, but let's go back to the Leetcode problem. We are given an array of strings called tokens that represent an arithmetic expression in a reverse Polish notation. We need to evaluate the expression and return the result of that expression. The valid operators are the addition, subtraction, multiplication, and division. Operands are integers. The division between two integers always truncates towards 0, and they make it easy for us by guaranteeing that there will not be any division by 0, that the input is a valid expression, and that the answer and intermediate calculations can be held in a 32-bit integer. So we need to define the function eval rpn that takes an array of strings. As we saw, we need a stack, and we need to go through the array of tokens from left to right. Because we have different types of token, we can use a switch to differentiate them. We have 4 different operators: the addition, multiplication, subtraction, and division. If we are not dealing with an operator, then it means that we have a number. When dealing with a number, because tokens are strings, we need to convert it to a number, and then we can push it to the stack. So let's say that we are given the tokens 3, 2, and plus. We are going to create an empty stack and then add the number 3 and 2 to the stack. Then when we meet the addition operator, we are going to pop the top of the stack and add it to the new top of the stack by popping it out. And then we push the result in the stack. For multiplication, it's the same idea. We pop out the last 2 elements of the stack, multiply them together, and push the result onto the stack. For the subtraction and the division, we need to be a bit more careful. Because if, for example, we have the tokens 3, 2, and minus, it means that we are evaluating the expression 3 minus 2. And the first element we pop is the right operand. and the second one is the left operand. So after storing the operands, we can apply the operation and store the result in the stack. For the division, it's the same idea, so we can store the last two operands in variables, apply the division, truncate the result, and push it to the stack. Once we're done evaluating the expression, the final result will be on top of the stack, so we can return it. And we don't need to check if it exists, because Leetcode tells us that there's at least one token. So let's run it, and we're done. So what do you think? Pretty cool, no? But handling parentheses would be nice. So that's what we're going to do when we will check out the Leetcode basic calculator problems 1, 2, and 3. Those will serve as baby steps before implementing our own programming language. So if that's something you would like to see, don't forget to subscribe. Bye, see you later.